All right, let's begin our second lesson for this unit. And to do that, let's go to our website here and take a look at section 5.2, which is graphs of polynomial functions. And so now what we're going to do in this second section is we learned a whole lot of new things about, in the first section, we learned a whole lot about linear, quadratic, cubic, quartic, and then any other even or odd degree polynomial. And so now we're actually going to put it into use and see actual questions that we're going to have to answer for that. And so our goal is to use your knowledge of the properties of polynomials to predict and sketch the graph of a polynomial. So we're gonna take into consideration all the properties we've learned, and then we're gonna try to sketch what a graph could look like for a polynomial. It won't be exact, it's just going to be a sketch. Okay, so let's get started by recapping what we did in the last lesson. So let's remember these definitions here, and let's have a discussion regarding these definitions. The degree of a polynomial, remember, is the highest degree, the highest of the degrees that have non-zero coefficients. So the highest of the degrees in a polynomial expression that, of course, has non-zero coefficients, right? Because if there was a zero coefficient, then that degree in that variable would never exist because it'd be 0 times something, and which would of course equal 0. So it's the highest of the degrees in a polynomial expression. Okay. The leading coefficient is the sign, which is plus or minus, in front of the coefficient with the highest degree. Okay, that gives us information. That tells us the direction that the graph is going in. So that's really important, the leading coefficient. The end behavior, if we were to define the end behavior, okay, quite simply, okay, it describes the trend of a graph when you look to the right and when you look to the left. Okay, so it describes, I like to say that it describes the trend of a graph when looking to the right, or when x approaches infinity, and then looking to the left when x approaches negative infinity. So what happens to y when that occurs? The domain, of course, is all our input values that are possible. So all possible input values, okay, from the x-axis. All right, so all the possible x values we can use in a function for a function. And the range, all possible output values, or y's, from the y-axis for a function. Okay, so that's just a quick recap of some of the terms and definitions that we've dealt with. Okay. Again, let's keep with the recalling or recapping what we did last lesson. So this particular graph here represents a linear polynomial function. Okay, its equation, I will tell you, is y equals x, or 1x. So a slope of 1, a rise over run of 1 over 1. Okay, with a y-intercept of 0, so just y equals x. This is any linear equation is a degree 1 equation, and for this particular graph, as x approaches negative infinity, y also approaches negative infinity, And as x approaches positive infinity, y approaches positive infinity as well. Okay? For a quadratic, the type here, of course, quadratic. The equation for this particular quadratic, I'll tell you, is y equals x squared. It's the parent function. The degree of our highest degree is 2. Okay? And the end behavior, as x approaches negative infinity, y approaches positive infinity. And as x approaches positive infinity, y also approaches positive infinity. So both there are approaching positive infinity. Okay, so that's all just to recap, going back over some of the terms that we learned. Okay. Still with the summaries, this is the table that I put in our last lesson. It's a great summary to have, and we're going to reference this for the following 2 questions, okay? So use this as a guide and as a reference. So here's a question that we're going to need to be able to answer for this lesson. Use degree and leading coefficient to describe end behavior of each polynomial. Okay, so we have to use the degree. Okay, so let's see here. Let's write out what our degree is. What is our degree of this equation? 5. Which tells me that this is going to be an odd degree. Okay. And our leading sign is what? Negative. Okay, that's important to note. Because now we have to describe the end behavior that's going to occur. And we can just use this table to kind of find things. But I mean, I'd like for you to understand and not just try to rely on the table so much. Okay, I want you to draw out what a potential sketch could look like for this. And then we'll look at the table to double check. So a potential sketch, okay, could look like this. Well, it's a degree 5. So from the last lesson, I know that they're gonna be pointing in the opposite direction here. Remember, all odd degree polynomial functions point in opposite directions. Okay? It's a degree 5, so I'm gonna have turning points. How many turning points will I have for a degree of 5? 4. It's always 1 less than the degree. And since my leading sign is negative, my curve is going to be going down and to the right. So these are all just little points that I'm making, down and to the right. And then later on, we will summarize what you're looking for. But this is going above and beyond. I mean, I can just use the table and kind of line things up with the table and what would happen with the end behaviors. But I think we're ready to do something like this where we analyze how many turning points we have, 1 less than the degree. I know that because it's an odd degree polynomial function, I'll have opposing end behaviors, okay? And since the leading sign is negative, it goes down and to the right. So let's draw something that goes down and to the right with 4 turning points. So start up here. 1, 2, 3, 4. Okay. Now we can easily write our end behaviors. Okay. Once you've got a sketch, it's easy to do because now you can say as x approaches infinity or positive infinity, y approaches, so as x is going to positive infinity, y is going where? Negative infinity. And as x approaches negative infinity, in this direction, y is approaching positive infinity. So rather than memorizing things, if we can simply take some of the properties that we know, draw a rough sketch of the graph, we should be able to figure out the end behaviors quite easily. Okay. Next example, let's try the same thing. So I know that the degree is 4. Let's try to be a little bit more organized. Degree of 4, which is even, which means that it's going to have the same end behaviors. same. So it's going to be, the two arrows are going to be pointing in the same direction. So same end behaviors. Okay. Turning points, since it's a degree of 4, we'll have 3 turning points. And direction, what's my leading sign? Positive, right? So it's going to go up. Okay, for an even degree polynomial, because they have equal end behaviors, the same end behaviors, a positive leading coefficient means the curve is opening upwards. Okay, there you go. That's our information in which we're going to be able to draw our sketch. Very rough sketch. So it's going to be opening up, degree of 4, 3 turning points. Okay, so ready? 1, 2, 3 turning points. Right, 1, 2, 3. So what is our end behaviors? As x approaches infinity, y approaches infinity as well. Okay, so as x approaches infinity, y approaches positive infinity as well. And as x approaches negative infinity, y also approaches positive infinity. So remember I said that they have the same end behaviors? They have the same end behaviors because y approaches positive infinity for both situations, right? For x going all the way to infinity and x going all the way to negative infinity. In each situation, we have y approaching positive infinity. So that's what I meant when I say that they have the same end behaviors. Okay? All right, moving on. Okay? State the sign. So this time we're given a potential graph. We're given a graph, and we have to state the sign of the leading coefficient, the domain and range, and then the end behavior. Okay? No problem. So first off, let's take a guess here at the degree of this equation. How can you figure that out? Look at the turning points. That's a dead giveaway. If you have 1, it's not the only thing, like there's more to it than that, but the potential is that this could be a 4th degree equation, but it could be more than that. It could be 6, it could be 8 as well. But let's go with 4th degree, but I mean, let's leave that out right now. Okay, let's not state that because I don't want to get into that just yet. Okay, let's just answer the question. Leading coefficient is positive. It's opening up. By the way, when I write the plus sign and then IVE, that means positive. Okay, the domain. Well, I know that all x values are possible for this function. Okay, for the range, not all y values are possible. Okay, so let's say that y is an element of real numbers such that, let's assume that this y value, let's just assume the scale is going by 1s here and that y value is -3. Okay, so this graph has a minimum point of -3, which means that my y values then must be greater than -3 or equal. They can equal -3. Okay, so greater than or equal to -3. Okay, now our end behavior. It's going to be just like the question above. As x approaches infinity, y also approaches positive infinity. And as x approaches negative infinity, y approaches positive infinity again. Okay, they have the same n behaviors. It's an even degree polynomial. And that's really what we should say about this, is that it's an even degree polynomial. Okay, and it should be noted that when I say that the number of turning points is always one less than the degree, okay, I should note the fact that that's the most turning points it can have. The most turning points it can have is one less than the degree, but it can have less than that. Okay, so and I forgot to mention that, it can have less than that. But the most that it can have is 4 turning points for this particular question for a degree of 5. So it's always, so the most it could have is 1 less than the degree itself, but it could have less. Like a degree of 5 equation doesn't have to have 4 turning points. Okay, it could have 2 turning points, for example. Okay, so keep that in mind, and that's where in the beginning of this question here I realized that I had forgot to mention that is the maximum number of turning points. When you look at the degree, the maximum number is always 1 less than the degree. Okay. Lastly, okay, you are going to be finding finite differences, so first, second, third, and fourth differences. I'm not going to do all of these examples because I did some in the last lesson. The one example that I did not do was a cubic function, so we're going to do the finite differences for this cubic function here. Okay, so let's find the first differences. Okay, then the second differences. And we know, we've already drawn the conclusion that if you have a cubic function, it's the third differences that will be constant. Okay, so we already know this. And this question just serves as the reminder of that. Okay, but let's find all the differences. You'll need some practice doing that. Okay, so here, -16 minus -2 is equal to -14. -54 minus -16, okay, is -54 plus 16, okay, which is -38. Running out of space there. Okay, next we have -128, and since I'm running out of space, I am just going to say what that is. Okay, so if we have -128, okay, minus -54, okay, it becomes -128 plus 54. Okay, so what does that equal? Okay, -74. And then lastly, -250 minus -128, which becomes plus 128. So we have -250 plus 128. Okay, and we have -122 there. So some pretty big values. So we have -122, -74, -38, and -14. Now when we find the second differences, we go in between, and we're now going to do -38 minus -14. So -38 minus -13, which is -38 plus 14. Now we're at -24. Okay. Then do -74 minus -38, which is -74 plus 38, which is -36. Then we're going to do -122 plus 74. I mean, it's going to be minus -74, but you get the idea. That becomes plus, and we're at -48. Okay, still, you can see the second differences are not constant, so we got to take them again, right? So let's go -36 minus -24, which is -36 plus 24, which is -12. Okay, and then -48 minus negative 36, which is negative 48 plus 36, okay, again, equals negative 12. And there you have it, constant third differences for a cubic function. Okay, so what conclusion can you make? We already know this. The conclusion that you can make, okay, is that the differences that will be constant corresponds to the degree of the equation. Okay, so first degree equations will have first differences constant. Second degree equations will have second differences constant, and so on and so on. Okay. Now, what conclusion can you make? This is new to us, right? What conclusion can you make about the sign of the leading coefficient and the finite difference? Okay, sign of the leading coefficient and the finite difference. Well, what you'll see is that in all of these examples, you have positive signs, leading signs here, okay? Except for this one, it was negative. And what you'll find is that the third differences, or the differences here, if you have a negative leading coefficient, your differences will also be negative. Okay, whereas if you have a positive leading coefficient, okay, you will have positive differences. Okay, so we should make note of that. That's something that's an observation that we should make note of. Okay, so if or when the leading sign coefficient is positive, the differences, the finite differences, will also be positive. Okay. So by looking at the finite differences, you can actually tell what direction the graph is going to go in. Because if they're negative, then you know the direction of the graph. If they're positive, then you know the direction of the graph. Okay, when the leading coefficient is negative, okay, the finite differences will be negative. Okay, so what did we do in this lesson? All right, what did we do? We used everything we learned in the first lesson. Okay, so terms like degree, leading coefficients, end behaviors, domains, and ranges. And we answered a question like this. This is the big one. So example 1, where if you are given an equation, are you able to write down the end behaviors based on some of the properties that we can get just by looking at the equation, right? For example, this one, we know it's a degree of 5, so it's an odd degree polynomial, which means they will have opposite end behaviors, okay? Now, since it's a degree of 5, the maximum number of turning points is 4. Not that that matters, okay? It still has opposite end behaviors, okay? And all we have to comment on is the end behaviors. The number of turning points doesn't really matter. The leading sign, if it's negative and it's an odd polynomial, it must be going down and to the right, okay? And so when you get all of those properties and you draw a rough sketch of what the graph looks like, it's then easy to determine the end behaviors, okay? So to summarize, you need to by looking at the equation, you need to figure out the degree, whether it's odd or even, okay? Even will have same end behaviors, odd will have different end behaviors. The number of turning points is irrelevant unless you wanted to draw like a more accurate sketch, okay? But then the other thing that's important is the leading sign. The leading sign is important with respect to knowing what direction the graph is going in, okay? So if it's an odd polynomial and it's negative, then the graph must be going down and to the right. If it's a positive odd polynomial, then it's going up and to the right. If it's an even polynomial and the leading sign is positive, the graph is opening up. Okay, if it is negative, then the graph is opening down. And that right there summarizes what you need to know for this lesson. Okay, so make sure you work on those homework questions and really get the hang of it, because this is an important thing that we did here in this lesson. Important question that will be popping up again in assignments and quizzes.